A light elastic string of natural length A and elastic constant K is fixed at one end to a point O on a smooth horizontal table. So here's the point O on a smooth horizontal table. The table is smooth, so there are no friction forces acting on masses on the table. A particle of mass m is attached to the other end of the string. So we have a particle attached here. We call it a particle because its dimensions are small compared to the length of the string. Ideally, it's a particle. We'll be looking at the motion of this end of the string, which we can take to be the same as the motion of the mass, because the mass is small. Initially, the particle is held at rest on the table at a distance 2a from O and is then released. So the particle has been displaced a distance a to the right from its equilibrium position. So now the length of the string is 2a. This distance here from O to this point is a, as we've seen already. So the point O corresponds to x equals minus a. So the particle has to be held here because the string has now been stretched and the string wants to get back to its natural length or its equilibrium position. So there's going to be a force acting on the mass. This force is the force due to the string. So the mass will move or accelerate to the left. So the mass is released, and we want to show that the time taken for the particle to reach point O is root m over k into 1 plus pi over 2. K is the elastic constant. That's analogous to the spring constant. We just refer to it as an elastic constant when we're talking about a string. We know from a previous video that the resultant force on this mass is entirely due to the string. There are no other horizontal forces acting because the table is smooth. So, there are no friction forces acting, and the two vertical forces cancel out. So that's explained in an earlier video. And by Hooke's law, the resultant force is a negative scalar times the displacement of the mass from the equilibrium position, x equals 0. So we covered all that earlier. We can even drop these arrows, as I explained before as well, because all the vectors are in one direction. So we can say f equals minus k times x. X and f are really vectors. Their signs give the directions. So if the vector is pointing to the right, it's positive. So this is the positive x-axis to the right. If the vector is pointing to the left, it is a negative vector. So if x happens to be positive, as it is here, then multiplying by this negative scalar, this is always negative, will give us a negative force. So you can see that the resultant force F string is pointing to the left for this position of the mass, for this particular position. But if the mass is on the other side, everything is reversed, of course, because x is pointing to the left and then F will be pointing to the right, and so on. So that's just all background. But what we really need to answer this question is the solution to this equation, and that was covered in a previous video. We saw the solution to this equation, that is, the position of the mass at any time, can in general be given by this sinusoidal function. Now, this particular form of the sinusoidal function is not particularly useful for us when analysing the motion of this mass. A better form is this. Write this as a cos of omega t. So I didn't explain this in earlier videos, but if phi happens to be pi over 2, then the sine of omega t plus pi over 2 is actually the same as the cos of omega t. So we can choose different values for phi. We can choose anything we like for phi and make this function, change the form of this function to this here. This is also a sinusoidal function. The fact that it's called cos doesn't change that. The cos function is referred to as sinusoidal. It has the same shape as the sine function. So this is a more general form to use when answering questions, solving problems, because usually what's given is that the position of the mass at time 0, that means its initial position, is equal to the amplitude. And that's what we get here if we plug 0 in for t, because the cos of omega times 0, well, we get the cos of 0, which is 1. So in many situations, or probably most questions that you see, you will find that the initial position x at time 0 is equal to the amplitude. And this form is ideal. Well, we could still use this form, of course. You know, we would have 0 plus 5, but we would have to make 5 pi over 2, because the sine of pi over 2 is 1. So if we could use this form and make 5 pi over 2, but it's easier to use this form here. Just say the position is a cos omega t. So then x at naught will be the amplitude. This is the amplitude, as you saw in earlier videos. Now, what is the amplitude of the motion of this mass? Well, it's the maximum displacement of this mass from its equilibrium position. Well, that's just this position here, which is a, well, little a. In general, the amplitude is denoted by capital letter A, but in this particular example, the amplitude is called small a. We know from previous videos that for a spring, omega is equal to root k over m, where k is the spring constant. Well, in this case, we're talking about a string, so k is the elastic constant, divided by m, that's the mass of the object attached. So we can write down our position function, x, as the amplitude, which we know to be little a, times cos of root k over m times t. So this gives us the position of the mass at any time t. However, I was talking earlier about this situation like as if we have a mass on a spring, and I mentioned when the mass gets to a position to the left of the equilibrium position, then the force is in this direction. I was talking about this formula here, that the force changes direction when the mass passes through the equilibrium position. However, this is a trick question, because what happens when the mass goes through the equilibrium position is that the string goes slack. We don't really talk about the compression of a string. I might have mentioned that earlier. So what happens when the mass reaches this equilibrium position is it just keeps going with the same velocity it had when it reached x equals 0, because there are now no forces acting on it. The string just goes slack, and assuming that this string doesn't actually get in the way of the motion. If there are no forces acting on an object, by Newton's first law, the object will continue with the speed it had at the instant forces on the object became 0. So the force becomes 0 when the object is at x equals 0. The string just goes slack. Okay, you might say there's other forces acting on you, its weight and the normal force, but they cancel each other out. We're talking about the resultant force on this mass becomes 0 when the string goes slack. So it is different from the case of a mass on a spring. That doesn't happen because the spring gets compressed and the resultant force changes direction. So that's the trick in this question. So to answer this question, we need to first of all calculate how long it takes the mass to go from the position x equals a to the position x equals 0. And for that, we can use this here, because this is valid for that part of the motion. So let's do that part first. We want to find the time t for when the position x becomes 0. So the time t for the mass to get to this position here, and then we will consider the rest of it. The rest of it is actually straightforward because the mass will go with constant speed. Right, so let's do that first part. Let's get the time taken for the mass to go from here to here. So what is that? What is the new position? It's x equals 0. So we set x of t equal to 0. So we want to find the time when x is 0, so we put this equal to 0. We divide both sides by a. So we just get cos of root k over m times t equals 0. To get root k over m times t, we get the inverse cos of 0. Now, the smallest value for the inverse cos of naught is 90 degrees, or pi over 2 radians. So this is the smallest value. And that's what we're interested in, because we're interested in the smallest time for the mass to go from its initial position, x equals a, to its final position, x equals naught. So t is got by taking pi over 2 and dividing by root k over m. So we divide pi over 2 by root k over m. That's the same as multiplying pi over 2 by 1 over root k over m. But 1 over root k over m is actually root m over k. We can invert k over m to get m over k. So that's the time taken for the first leg of the journey. That's the time taken for the mass to go from its initial position at x equals a to this position x equals 0. Now we need to find the time taken for the mass to go from x equals 0 to here. We know that it will travel with constant velocity because the resultant force on it is 0. By Newton's first law, it will not accelerate. It will keep going with the speed it has when it reaches x equals 0. So the first question is, what is the speed when x equals 0? So we want the speed, which I'm calling v, when t equals root m over k times pi over 2. It's easier to find, well, once we have the time, we can get the speed, because the speed will depend on the time. How do we get the speed? Well, we get the speed from the position. The speed at any time, I could write v of t to emphasize that v is a function of t, but we don't have to put that in. V is the derivative of x with respect to time. That's distance x over time, distance traveled over time taken. So we just differentiate this here. So this is our x of t, differentiated with respect to time. Well, the derivative of the cos function is minus sine. And by the chain rule, we must multiply by the derivative of the angle. The derivative of root k over m times t with respect to t is just root k over m. It's just the coefficient of t. Of course, we bring that root k over m to the front, so we get minus a times root k over m times the sine of root k over m times t. So that's the speed at any time t, but we want the speed at this particular time. So we need to plug this value in for t. So this is what we get, plugging in this value of t in here. Now, root k over m times root m over k is just 1. So we get the sine of pi over 2. Well, that's sine of 90 degrees, which is 1. So we have minus a times root k over m times 1. So we just get this. So that's the speed at x equals 0. And we know that the mass will continue with this speed until it reaches point O. So what distance will it travel? Well, it travels a distance of a with a constant speed of minus a times root k over m. So we need to find the time taken. Well, we know that when an object travels at constant speed, the speed is just the distance over the time. I'll write d for distance and t for time, which means that we can rearrange this to get t equals d over v. So the time taken is the distance over the speed. The speed is constant. So d is a, and the speed is, well, we have a negative value here, indicating that we have a velocity. Speed is always positive, but this quantity is actually negative. Root k over m, we're assuming we're getting the positive square root. A is meant to be positive. The amplitude is normally taken to be positive. A is the amplitude in this case. So this is a negative quantity. So it's a velocity. Velocity can be positive or negative. Velocity in one direction. So to get the speed, we just get the magnitude of this. So we just make it positive. So I could emphasize that we're getting the speed by showing the magnitude of v, put vertical lines around v. Anyway, that's only a small point. And these a's cancel, so we get 1 divided by root k over m. Well, that's equal to root m over k. So that's the time taken for the last leg, or the second leg of the journey. So for the first leg, the time taken is this, and for the second leg, the time taken is root m over k, and we have to add these two times together. So we add the two times, we can factorize out root m over k, so we've root m over k into pi over 2 plus 1, or we can write it like this. This is the way it's given in the question.